Welcome to Logical Verification 2020 to 21. This video is about Chapter 12, Section 2, type classes with two binary operations. So in the last video, we've seen lots of structures like semigroups, monoids, groups that have a type with one binary operation and maybe some additional elements of the type like 1 or 0 and worse. However, many structures have two such binary operations. Well, for example, think of, the rational numbers with the plus and the rational numbers with the times. So, like rational numbers with plus, that's an additive commutative group, and the rational numbers with the multiplication is a commutative monoid. So, however, these are not just useful as two separate structures, but there are also axioms, laws that hold for the combination of plus and times, such as, for example, distributivity. So that when we have an addition and multiply with some element on the right, then we can pull the multiplication inside, and also on the other side. Okay, so lots of these structures, and this is not just the rational numbers, but it's also the natural numbers have this axiom. And so there's a lot of structures that have like both a plus and a multiplication operation, and typically these operations fit together very nicely. So this is distributivity, this is right distributivity, there's also left distributivity with the addition on the other side. And another interesting axiom is that x times 0 should be 0, which also combines stuff from the plus. So the property of the plus, namely the 0, that we're talking about the 0, which is the neutral element for plus, as well as the multiplication, which comes from the other structure. And just as we had this hierarchy of semigroups, monoids, groups, we also have here another hierarchy of semi-rings, rings, division rings, fields that have progressively more axioms and more structure. So, so a semi-ring is a structure where the plus is an additive commutative monoid and the multiplication is a monoid. There is one additional axiom here in addition to distributivity. So the additional axiom is, of course, that x times 0 is 0 times x is x. This is another property that we already have in a semi-ring. Then the ring extends this by having the plus operation be an actual group, so that there is a minus here, and then we have a division where we have an inverse for the multiplication, well, for all elements except 0, and we have field where the multiplication is in addition commutative, and then there is always a commutative version of semi-rings and rings as well, where the multiplication is commutative. So in a sense, field is a commutative division ring. And I see there is something completely outdated here. We no longer have a discrete field. Instead, already division rings have this property that that the inverse of 0 is 0, and also x divided by 0 is 0. This is a very, very useful design choice, making division by 0 well defined, and it should return 0. This makes a lot of nice theorems true, or at least true with few assumptions. So, for example, you have that x times x to the minus 1 is x, and this is true for all x in the division ring. Just as a consequence of making division by 0 well defined. So this is really useful, and hence we now have this for all of those structures. Okay, good. it's a similar hierarchy to what we have for a single binary operation. Right. You can look at the source. It is defined, as you would expect. It's a type class with one type, and the type class extends for field. It extends a commutative ring with an inverse, and it has at least two elements, which is what non-trivial means. And really, this is the important axiom. The inverse of 0 is 0. So this is true for everything that we have here. Okay, so in the last video, we had an example with the integers modulo 2. So this type is Z2. And now let us also define a multiplication on it and turn it into a field. So this is the smallest field. It's the field with two elements. And right, the multiplication is defined as you would expect it. If you have a 1 on either side, it returns the other element, as it needs to do in a field. And 0 times 0 is 0. Okay, this is also how the multiplication needs to look like. And 1 and the inverse also zero. So the inverse in Z2 is just the identity. So the inverse of 0 needs to be 0 because that's the convention that we have. And the inverse of 1 also needs to be 1. Right? This also is true in every field. Okay, and then we just need to prove lots and lots of properties. Just as we did for the add group instance, this all goes by case batching. Like cases on everything, there are just two elements, so we just need to consider all cases. And once we've done this, we have all the operations available. We have multiplication, we have division, we have minus on our new Z2 type. And not just that. By defining an instance such that the type becomes an additive group or a field, it allows us to use automation tactics that work for any field or additive group. And there are quite a few of such tactics that we have in MATLAB and Lean. So the first one is ring. This works in every ring. No, in every commutative semi-ring. Always look at the documentation. And what it does is it proves any equation that is true in a ring, in general, like just with an equation that follows from the ring axioms. So, such as, for example, the following: a plus b to the third is this here where you multiply it out. And then ring proves such equations. So when you give an equation that is not true, it will actually give you a fairly nice error message. It simplifies both sides, and then you can spot the error. There's several modes that you can use to customize this output here. Check out the documentation. This is a good idea. And then try out the options. So this works if the exponent, this power operation here, only has numerals as arguments. When the exponent operation has more complicated terms as arguments, this might fail, because strictly speaking, this is no longer in the language of a ring. So there is an extension of ring, which is called ring exp, which also works with terms where the exponent is more complicated than numeral. Okay, so this is what we have for rings. This is very useful. But we also have automation that works for groups. So which one is it exactly? So it works in additive, commutative monoids and groups. This ABO tactic. And well, again, it works for the integers because they are an additive commutative group, but they also work for our new type here, because it is also an additive commutative group. Just by defining this very small instance, we get a lot of automation for